Hi, hello everyone. Myself, Chandan, working in Tumkur University. In this lecture, I discuss on complex analysis. And in complex analysis, I discuss what to mean by Cauchy's inequality, Liouville theorem, and fundamental theorem of algebra. And I already uploaded these three concepts in a separate videos, but now I combine all these things, all these concepts, and uploading in a single video. So, and I suggest everyone before watching this video, you must know what to mean by analytic functions, what to mean by complex valued. First of all, what to mean by complex valued functions, what to mean by analytic functions, how to evaluate integrals in complex form, and how to mean by line integrals. If you know all these things, it will be easier. So, what do you mean by Cauchy's inequality? Firstly, we concentrate on Cauchy's inequality. What do you mean by Cauchy's inequality? Statement of Cauchy's inequality is if f of z be any analytic function inside and on the circle C with center at z is equal to a and radius r. First, function is analytic which is inside and on any circle C. Circle C means which is center is z is equal to a and radius r. Then this holds fn of a, f power n of a, which is nothing but nth derivative at a point a, is less than or equal to m into n factorial divided by r power n, where n is 0, 1, 2, 3 up to natural numbers including 0. And m is a positive number such that f of z is bounded. F of z is bounded for all z on this circle. On this circle, f of z is bounded, then this inequality holds. F of z be analytic inside another circle C with center z is equal to a and radius r, then this inequality holds, where this capital M is any positive number such that f of z is bounded on this circle. So let us understand the proof of this theorem. To prove this theorem, I use Cauchy's integral formula. So what do you mean by Cauchy's integral formula? F power n of a is equal to n factorial divided by 2 pi integration over any curve C or over any circle C into f of z divided by z minus a whole power n plus 1 into dz. This is the Cauchy's integral formula. We have to prove that absolute value of f power n of a. This holds for n is equal to 0, 1, 2, 3, so on up to infinity, where this is a natural number. So to prove this theorem, I use Cauchy's integral formula. The Cauchy's integral formula is f power n of a is equal to n factorial divided by 2 pi into integration of this thing. So we have to find the absolute value of this, where this is a is circle C with a is a center and radius is r. This is r power n, is nothing but radius. So f power n of a, to find this absolute value, so apply modulus on both sides. Apply modulus on both sides, then f power n of a is equal to n factorial divided by 2 pi into integration over c f of z divided by z minus a whole power n plus 1 into dz. So, and we have from one property on this line integrals, modulus of integration of f of z is less than or equal to integration of modulus of f of z. So, to use this property, we have f power n of a, this is f of z, modulus of integration of f of z is less than or equal to integration of modulus of f of z. Therefore, this equality becomes less than or equal to n factorial. Modulus of a into b is nothing but modulus of a into modulus of b. Therefore, apply modulus of this. Suppose this is a into b is nothing but modulus of a into this is modulus. But this modulus is less than or equal to integration of modulus of f of z. Therefore, f power n of a is less than or equal to modulus of n factorial divided by modulus of 2 pi into integration over this circle C, modulus of f of z divided by z minus a whole power n plus 1 into dz. So, which is less than or equal to n factorial. This is again a positive number, therefore modulus is same as that, n factorial divided by modulus of 2 pi is nothing but modulus of 2 is 2, modulus of pi is pi. This is again a positive number. You can calculate the modulus, you will get the same number. Modulus of 2 is 2, modulus of pi is also pi. But modulus of I is nothing but 0 plus I into 1. So root of real part square plus imaginary part square. Real part is 0, imaginary part is 1, which is nothing but 1. Therefore, modulus of I is nothing but 1. Integration over every C. But given in statement, f of z is less than or equal to this m, where m is any positive number. Therefore, f of z, modulus of f of z is less than or equal to this m. Modulus given f of z is, modulus of f of z is less than or equal to m. So I use this bounded n factorial divided by 2 pi into integration over inequality m into modulus of z minus a whole power n plus 1. But we already know that z minus s, z is any circle with center at z is equal to a and radius r. Then modulus of equation of circle in complex form is nothing but with circle with center is a and radius r. Then equation of circle in complex form is modulus of z minus a is equal to r. So I use this definition. Modulus of z minus a is nothing but r. So n factorial divided by 2 pi into integration of m divided by r power z minus a is nothing but r. This is again modulus of this whole power n plus 1. Therefore modulus of z minus a is nothing but r power n plus 1 into modulus of dz, which is again less than or equal to, in fact this is constant, so take outside, n factorial into m divided by 2 pi into r power n plus 1 integration over n equal to c. But circle is c, therefore circle equation is modulus of z minus a is equal to r. So to remove this modulus, which is nothing but z is equal to a plus r into modulus of z minus, mod z is nothing but absolute value is nothing but r into e power I theta. Therefore z is equal to a plus r into e power I theta. Integrate this with respect to theta. Therefore dz, we get dz is equal to r into, this is constant, sorry, differentiate this with respect to theta. So dz is equal to r, this is constant, differentiation is 0, this is r is also constant, take it as common, and e power I theta, differentiation of e power I theta is e power I theta into I into d theta. And this is a circle, therefore theta varies from 0 to 2 pi. So use this. So take modulus for this function, for this. So modulus of dz is nothing but r into modulus. Modulus of r is nothing but, which is a positive number, we get the same modulus. R is nothing but r, modulus of I into e power I theta. Therefore modulus of I into e power I theta is nothing but modulus of I, which is nothing but 1. Modulus of e power I theta is nothing but root of cos square theta plus sin square theta, which is again 1. So modulus of dz, we get modulus of dz is equal to r into d theta. So n factorial m divided by 2 pi r power n plus 1 into integration over n equal to c. So c varies from 0 to 2 pi. Modulus of dz is nothing but r into d theta. So use this. F power n of a is less than or equal to n factorial m divided by 2 pi r power n plus 1 into 0 to 2 pi r into d theta. R is again a constant, take outside. This r and this r power n plus 1 get cancelled. Therefore remaining is n factorial m divided by 2 pi r power n. So this is integration 0 to 2 pi 1 into d theta, which is nothing but theta, and the limits is 0 to 2 pi. Therefore we get 2 pi itself. Therefore which is less than or equal to n factorial m divided by 2 pi r power n into this, we get integration of this is nothing but and substitute these limits, we get 2 pi. So 2 pi get cancels. Therefore f power n of a is less than or equal to n factorial m divided by r power n. N factorial m divided by r power n. This is nothing but statement of Cauchy, f of z, any analytic function which is inside and any circle c, center z is equal to a and radius r, then f power n. This is holds for all n belongs to natural number including 0. So f power n of a is less than or equal to n factorial into m divided by r power n. So next I discuss Liouville theorem. What is Liouville theorem? The statement of Liouville theorem is, if f of z be analytic and bounded in the entire complex plane, then f of z is constant. This is nothing but any function which is analytic and bounded in the entire complex plane, then that function is constant. Or in other words, the only function which is analytic and bounded in the entire complex plane is constant functions. In some definitions and in some textbooks they have used entire function which is bounded is nothing but constant function. The definition of entire functions is any function which is analytic everywhere in the complex plane is nothing but entire function. And to prove this Liouville theorem, I use previous result, that is nothing but Cauchy's inequality. So the statement of this theorem is, f of z be analytic and bounded in the entire complex plane, then that function is constant. So to prove this theorem, I use the previous Cauchy's inequality definition. And given f of z is bounded, f of z is bounded in the entire complex plane. But data f of z is bounded in the entire complex plane means for all value of z in a complex plane. So f of z is bounded for all value of z. Thus, bounded definition of bounded is, thus there exists a real number m such that f of z is less than or equal to m for all z. And To use the Cauchy's inequality definition of Cauchy's inequality is f of z be analytic on any circle C with center z is equal to and radius r. If we get any circle f of z be analytic on any circle, since we have f of z is bounded for all value of z, f of z is bounded in entire complex plane, then and in particular if we take any circle on C, any circle on complex plane, then f of z is also bounded. So in particular f of z less than or equal to m for all z in and on the circle, any circle with center z is equal to n radius, because f of z is bounded in the entire complex plane. Since f of z is bounded in the entire complex plane, if we take any circle C with center z is equal to a and radius r, then that in the circle also f of z is bounded. So f of z is bounded on this circle. And to use this Cauchy's inequality, and given f of z is analytic, on complex plane, means f of z is analytic on this circle also. F of z is analytic on this circle and f of z is bounded on this circle. Hence by Cauchy's inequality, f power n of a is less than or equal to m into n factorial divided by r power n. In particular, if you take n is equal to 1, then f dash of a is less than or equal to m into n factorial. N factorial nothing but 1 factorial nothing but 1. R power n is nothing but r power 1 is nothing but r. So f dash of a is less than or equal to m divided by r. But we apply this for circle with center z is equal to a and radius r. But given f of z is bounded, f of z is analytic and bounded in the entire complex plane. So we extend this to entire complex plane. How to extend this to entire complex plane? As radius tends to infinity, we are choosing the entire complex plane. Hence, as radius tending to infinity, f dash of a is less than or equal to m divided by r. This is true by Cauchy's inequality. And as if we extend this to whole complex plane, as r tends to infinity, this is any positive number divided by infinity, which is nothing but something like, suppose m is nothing but 1, then 1 by infinity is nothing but 0. Then m by r power n tends to 0. As radius tends to infinity, m by r tends to 0. Therefore, f dash of a is less than or equal to 0. F dash of a, where a is any arbitrary center, any circle with center z is equal to a and radius r. Therefore, this tends to f dash of a is less than or equal to, this is modulus, absolute value. Absolute value is always greater than or equal to 0. If we get absolute value is less than or equal to 0, mean absolute value must be is equal to 0. Therefore, f dash of a is equal to 0. F dash of a is equal to 0, which is nothing but f dash of modulus f dash of a is equal to 0. If you apply modulus, we get the same result. Therefore, modulus of f dash of a is equal to 0, which is nothing but f dash of a is equal to 0. But a is arbitrary. Any circle with center on any part of a complex plane. Therefore, since a is arbitrary, we can choose it as f dash of z is equal to 0 for all value of z. For all value of z, this result holds. What is the definition of constant functions? If f dash of function is said to be constant at that point, means f dash of that point is equal to 0, then f is said to be constant at that point. But here f dash of z is equal to 0 for all value of z. For all value of z means in entire complex plane f dash of z is equal to 0, which is nothing but f of z is constant. Therefore, given definition, f of z be analytic and bounded in the entire complex plane, then f of z is constant. So we are choosing f of z is the given data f of z is bounded. We are choosing this, and to apply Cauchy's inequality, we are choosing any circle center z is equal to a and radius r. Hence, any function which is analytic and bounded in the entire complex plane, then those functions are nothing but constant functions. So these are equivalent definitions. We have some equivalent definitions, or you can say as a results, which is nothing but you can use this definition as this result as a definition for Liouville theorem. So any bounded entire function is, I already said what is my entire function. Any function, any complex function which is analytic everywhere in a complex plane, then that function is nothing but entire functions. So any bounded entire function, the definition of Liouville theorem is analytic and bounded in the entire complex plane, that function is constant, which is nothing but any bounded entire function is nothing but constant. Or if you have any non-constant function, non-constant entire function, then that function must be unbounded. This result, bounded entire function is constant. Suppose it is a non-constant and entire function, then that function must be unbounded. You can take example as a e power z. E power z clearly, which is clearly which is non-constant and which is analytic in entire complex plane, and we already know that e power z is bounded. Then the definition of other definition of constant function is nothing but the range of any constant function is nothing but singleton. So if we have any bounded and entire function, then the range is nothing but singleton. So the application of this theorem is very important in complex analysis. And let us move on to the fundamental theorem of algebra. What is my fundamental theorem of algebra? What is my fundamental? It has many applications, and the results of the statement of fundamental theorem of algebra is every polynomial equation. This is a polynomial equation f of z is equal to a0, a1 into z plus a2 into z square plus a3 into z cube plus so on up to an into z power n, where n is greater than or equal to 1 and an not equal to 0. This a0, a1, a2, so on up to an are maybe real or complex coefficients, and an not equal to 0 and n is greater than n. Clearly this is non-constant. If n is equal to 0, then this may be constant. N is greater than or equal to 1 means this may be minimum degree 1 polynomial equation of degree 1. So every polynomial equation f of z is equal to a0 plus a1 into z plus a2 into z square plus so on up to an into z power n, n is greater than or equal to 1, n not equal to 0, has at least one root. And you can prove that it has at least one root mean, which is nothing but it has exactly n roots. Every polynomial equation, a very nth degree polynomial equation has exactly n roots. The roots may be real or complex. So to prove this theorem, I again use this Liouville theorem applications of Liouville theorem to prove the fundamental theorem of algebra. So by using contradiction method to prove this theorem. So suppose f of z is equal to, so we have given f of z is a non-constant. F of z has at least one root. Suppose it has no roots. It has no roots means suppose f of z is equal to 0. Suppose f of z is equal to 0. F of z is equal to 0 at least one point of z, then it has at least one root. Here suppose f of z is equal to 0 as no roots mean f of z not equal to 0 for any z. Suppose f of z is equal to 0 for at least one z, then that is the root of this polynomial. So let us assume contradiction method. F of z is not equal to 0. F of z not equal to 0 for any z mean f of z has no roots. We are assuming f of z has no roots. If you arrive this is a contradiction, then we say that f of z has at least one root. The root may be real or complex. Suppose f of z is not equal to 0 for any z. F of z not equal to 0 and given f of z is a polynomial function which is analytic everywhere. Since f of z is analytic, then if we choose another function which is nothing but reciprocal of this function, then that function is also analytic. By using algebra of analytic function, f of z not equal to 0 for any z, we have choose another function g of z which is equal to 1 by. Since f of z is analytic everywhere and 1 is nothing but constant, by using algebra of analytic functions, we have choose another function which is 1 by f of z. This is analytic, this is also analytic, hence this whole 1 by f of z is analytic for all value of z, because given f of z is a polynomial, which is not polynomial functions are analytic everywhere. Therefore g of z is equal to 1 by f of z is analytic for all value of z. As z tends to infinity, this is again polynomial, hence f of z tends to infinity. As z tends to infinity, f of z is also tends to infinity. So let us choose another function g of z is equal to 1 by f of z. As z tends to infinity, f of z tends to infinity, hence 1 by infinity is nothing but tends to 0 as z tends to infinity. Hence g of z tends to 0 as z tends to infinity. G of z is again a function. As z tends to infinity, g of z tends to infinity mean g of z is bounded for all values. Since it is analytic for all values of z, and g of z is bounded as z tends to infinity mean g of z is bounded for all value of z. So f of z is equal to 0 using contradiction method. F of z not equal to 0 for any value of z, since g of z is bounded for all value of z, and g of z is analytic and g of z is bounded. Revise what I say in Liouville's theorem. The statement of Liouville's theorem is f of z is analytic and bounded in the entire complex plane, then that function is constant. So here we are arriving g of z which is analytic for all value of z and bounded for all value of z, any function which is analytic and bounded in the entire complex plane, then that function is constant. This is a statement of Liouville theorem. Hence here g of z is analytic and bounded for all value of z means in the entire complex plane. Hence g of z must be a, by using Liouville theorem, g of z must be a constant. Since g of z is equal to 1 by f of z, since g of z is constant, then f of z is also constant. Since f of z is a constant function, which is a contradiction. They are given f of z is a polynomial. Clearly polynomial functions are not constant, but we are arriving that f of z is a constant function. This is a contradiction to our assumption that f of z has no roots. Hence, which is a contradiction to our assumption that f of z is a polynomial of degree greater than or equal to 1. Hence, f of z is equal to 0. We are arriving. First, we assume that f of z not equal to 0 for any value of z, but we are arriving at it's a contradiction. Hence, f of z is equal to 0 for at least one value of z. F of z is equal to 0 for at least one value of z mean f of z is equal to 0 for at least one value of z mean then that value acts as the root of that polynomial. Hence, f of z is equal to 0 as at least one root. F of z is equal to 0 as at least one root. Every polynomial equation f of z a0 plus a1 into z plus a2 into z square n greater than or equal to 1, a not equal to 0 as at least one root. So we proved that f of z is equal to 0 as at least one root. So thank you everyone.